now we need to, in order to understand how this radiation interacts with matter in different ways, is describe radiation in terms of energy. And the way this was done was, is there was certain phenomenon that we see with electromagnetic radiation, such as the formation of rainbows, that indicate that electromagnetic radiation behaves physically like waves. But there's other properties of radiation that led the scientists who were studying this 100 years ago or so to need to express or explain electromagnetic radiation in terms of particles. And so it was actually Max Planck who postulated that because light can interact with certain matter and cause chemical changes and also cause electrons to move out of the atomic sphere, that they must have different energy associated with them. And so Max Planck was the first one who said that actually the energy associated with electromagnetic radiation is quantized. Okay? He used the word quantized. And what that means is that the energy is not continuous, but that the energy associated with light is actually bundles of energy. It's not a continuous spectrum of energy, but it's quantized bundles of energy. And the difference between those individual bundles of energy from one type of electromagnetic radiation to the other is very, very tiny. The difference from one wavelength to the next, for example, the amount of energy associated with it was very, very tiny. Nevertheless, there was a difference, and it was not a continual change. And so then it was Einstein. Well, Max Planck was the one who said that it should be quantized in some way. Einstein is actually the one who described light as photons. And so photon is the way we describe the particle nature of light. Wavelength or frequency is the way we describe the wavelength part of light. And it's very confusing, granted. People do not still completely understand why electromagnetic radiation has both properties of wavelengths and properties of particles, because there is no mass associated with with electromagnetic radiation. All right, so Einstein actually won the Nobel Prize for this description and this model of light, the photon model of light. He didn't win the Nobel Prize for the theory of relativity, which is where we got the E equals mc squared, the mass-energy relationship. He won it for this, describing light in terms of photons. And that equation that he used to relate the amount of energy associated with electromagnetic radiation of a certain wavelength is this equation right here. E equals hc over lambda. And because of the relationship between the speed of light and the wavelength and the frequency of light, it's also sometimes expressed as E equals h nu. So you can describe it in terms of the wavelength of the light, that is the energy of the photon associated with that, or in terms of the frequency of the light, whereas wavelength is frequency, lambda is wavelength and nu is frequency. Anyway, this is equal to this is equal to that. But h is a constant called Planck's constant. Okay. And the value of Planck's constant that he worked out, and see, when he was working out, Planck was working on his constant, and he was working on this relationship, he didn't quite understand the significance of his constant. Einstein's the one who really explained the significance. So even though Planck came up with it, Einstein explained it. That's why Einstein gets a lot of the credit. But Planck gets his name on the constant. But anyway, it is 6.626 times 10 to the negative 34 joules times seconds. That's the unit. Okay, that's a constant that makes this relationship true. E equals h nu. It's the relationship directly between the frequency and the energy of the photon, or the wavelength. And if you want to correlate to wavelength, then you also have to add in there c, which is the speed of light, which we've seen before. The speed of light in a vacuum. And that is widely taken to be 3 times 10 to the 8th meters per second. Alrighty, so now you have this relationship to where you can see that the higher the frequency or the lower the wavelength, the shorter the wavelength, and the higher the frequency, the more energy is associated with that particular wavelength of light. All right, so now we have this nice relationship between the energy of the photon associated with the light given a particular frequency or wavelength. All right, this was a revolutionary idea. It helps predict how energy is going to react with matter. Just think about it. The higher the energy of this bundle of energy colliding with matter, the more damaging that light or that energy associated with the electromagnetic radiation is going to be to whatever it collides with. So the higher energy is more damaging. That's why gamma rays, X-rays, and ultraviolet rays, that's on the higher energy end of the spectrum. All those forms of radiation are considered ionizing radiation because it's enough energy associated with those photons, those little bundles of energy, to knock an electron out of a covalent bond. All right, so once you knock an electron off, you've disrupted your charge balance, and that's why it's called ionizing, because you're forming ions when that type of radiation interacts with matter. All right, so now we have an equation that relates, and another way of describing electromagnetic radiation. It is simultaneously described in terms of wavelength and in terms of particles, and its behavior is probably truly somewhere in between, but that's as best as we can model and explain it right now. All right, I am not going to work any problems, but what I want you guys to do is on, let's see which homework. I can't remember which homework it is. Shoot, I didn't write it down, but on your homework that's associated with this particular lecture, I think it's homework 7, but you can double check with your teacher. I'll write it down somewhere for them. I'm going to put some problems where you need to convert like wavelength to frequency and vice versa, some conversion type problems. And also, given either this or that, a wavelength or frequency, I want you to be able to calculate energy. And given energy, I want you to be able to calculate either wavelength or frequency. Just practice using these equations. It's not super critical for this class, but I do want you to go ahead and try it on your own in your groups. And I'll give you some homework problems to motivate you to do that. Because if you do end up going on and taking chemistry in college, this is something that is sort of expected, that you understand the energy and how to calculate the energy associated with different forms of electromagnetic radiation, because then you can directly correlate that then to a lot of chemical changes and physical changes that occur. And so just having practice and being real familiar with these equations will just save you some headache and heartache later down the road. But I don't want to take time to work it. It's just basic plug and chug algebra. But the common mistakes that are made is that not putting your units into meters for the wavelength, okay? Because the speed of light that is really the constant that relates wavelength with frequency, so you have to have your wavelength in meters before you calculate the energy, okay, or before you calculate the frequency. Okay, so that's something you can do on your own, and if you guys want to stop and practice that now, you can, or at the end of this lecture before the next lecture, you can practice in small groups. I'd like for you guys to work on them in small groups. Since I'm not giving any examples, y'all can work it out together and help each other overcome the common mistakes.